In this lesson, we are going to learn about the chemical analysis of combustion analysis. That is, we are going to use the chemical reaction of combustion in order to understand about the chemical formula of a substance. So in this case, what we have here is the process of combustion analysis. And if we look at the chemical reaction of combustion, we would have a sample of hydrocarbon, and this hydrocarbon is treated with excess amount of oxygen, so they both react, and this process is called a combustion reaction. And in this type of chemical reaction, it will always produce water and carbon dioxide gases. So we have two types of gases being produced, water and carbon dioxide. So what we have here is this. We are going to have two chambers that are responsible for absorbing specific type of gas. I have my water absorbers, and in this case, it's all pre-weighed. So we would know exactly what is the initial mass going to be. So as a combustion reaction occurs here, it will produce carbon dioxide gas and water gas as well. So once those gases escape, it will be captured, in this case specifically for water in this chamber, and in this case carbon dioxide will be absorbed. So if we look at the changes in mass of the absorber, that changes in mass is also the mass of water being produced. The same thing for carbon dioxide. If there is a change in the mass of carbon dioxide or absorber, that change is actually the mass of carbon dioxide gas being produced. Now if we look at this, if I know the mass of water, and if I know the mass of carbon, specifically looking at water, I can actually solve for the mass of hydrogen in the substance using basic stoichiometry flowchart. The same thing for carbon dioxide. If I know the mass of carbon dioxide, I can actually solve for the amount of carbon in this substance using all basic stoichiometry flowchart. So now if we have a substance that contains other elements that are neither carbon nor hydrogen, we have to do different analysis in order to determine the percentage by mass or the mass of that specific element. And of course, the nature of the problem becomes more complicated if there are other elements in this substance. So let's look at a specific example. I have a combustion of a compound consisting only carbon and hydrogen, cause a 3.31 grams increase in the mass of carbon dioxide absorber and a 1.03 grams increase in the mass of water absorber. What is the empirical formula of the compound? So first of all, we know that this compound only have carbon and hydrogen. And because there are increase in the carbon dioxide absorber and the water absorber, we know this is the exact amount of carbon dioxide being produced. And in this case, this is the exact amount of water being produced. So what we have here is 3.31 grams of carbon dioxide being produced. So using stoichiometry, we can convert and find moles of carbon. And here is the flowchart. We have our given mass times the molar mass conversion factor and times the mole ratio, which is within the chemical formula. And of course, the molar mass of this carbon dioxide is 44.01. And for the mole ratio, it's basically moles of A and moles of B. And in this case, we're looking at the mole ratio within the chemical. In this case, A's are given CO2 and B is carbon. So for CO2, just 1, and for carbon, in this case, just 1. So what we have here is this. We have a given mass times the molar mass conversion factor of the gram on the bottom, so it cancels out. And of course the moles on top, and because that is moles of CO2, down here must be mole of CO2, cancel it out. And what we have here is 0.0752 moles of carbon. And then for the same thing with water, we have a given mass of water, that is the increase in the mass of the water absorber. So based on the stoichiometry flowchart, we have a given mass of water times the conversion of molar mass. Notice how I have 18.02 grams of O2 on the bottom. To cancel out the gram, we have moles of water. And in this case, if we look at water, there are 1 moles of water but 2 moles of hydrogen. That's where I get the 2 from. So the moles of water cancel out, give us these two values. Just like solving for empirical formula, what we have to do is divide by the lowest number of moles. In this case, this is the lowest number of moles, so 0.0752. 0.0752. This gives us 1, of course, and this gives us 1.5. How do we get rid of the 0.5? Multiply them all by 2. So what we have here is 2, and this is 3. So our formula is C2H3. That is our empirical formula. Now let's try another problem. We have a combustion of a compound, consists only of carbon and hydrogen again, causing a 3.31 milligrams increase in the mass of carbon dioxide absorber and a 1.03 milligram increase in the mass of water absorber. What is the empirical formula? Notice how this question is very similar to this question, except that I have milligram and gram. And in this question, you are going to learn this trick. That is, if we have milligrams, or whatever unit it is, as long as it is consistent, you can actually change the ratios in the stoichiometry to that specific unit. In this case, if I have milligram, let me show you. So we have milligrams of carbon dioxide. What we can do is now think of millimole. Notice how I don't want to convert this to mole, but I convert this to millimole. Because in the end, we are looking for the ratios of mole. So it doesn't matter if it's in the unit moles or milli or kilomole, as long as they are consistently in the same unit. So if I keep this milli unit, so if I keep the prefix milli, I would apply this to all of the conversion factor in the stoichiometry. So for example, I have 3.31 milligrams of carbon dioxide. I will convert to millimole. And look at my conversion factor. I have milligrams of carbon dioxide times by the conversion factor of molar mass, but in this case, I look at in terms of milli. So we have number of milligram equal to 1 millimole of A times the number of millimoles of A equal to the number of millimoles of B. So I have milli instead of just mole. So how does that work? Let's look at specifically the molar mass. So I have 3.31 times milligrams of carbon dioxide. And notice how I have 44.01 milligrams carbon dioxide. And I have 1 millimole. And in terms of ratio, if I take the milli away and have moles and grams, it would have the same ratio equal to 1. So I have 1 millimole of carbon equal to 44.0 milligrams of carbon dioxide. That is still equal to the same values. So that's the beauty behind manipulating unit. And the same thing, we have 1 millimoles of carbon equal to 1 millimoles of carbon dioxide. So this is a great tool for multiple choice. And then I do the math. And if I substitute this in the calculator, of course, let's cancel out the unit. Our answer would be in terms of millimoles of carbon. Now let's do the same thing to water. So in this case, we have milligrams of water. So let's solve for millimoles of hydrogen. So again, when we look at the ratio, as long as the unit are the same, it doesn't really matter. So for water, what we have here is 1.03 milligrams of water times, notice how I have 18.02 milligrams of water. Of course, it's going to be relative to 1 millimoles of water. And the milligrams of water cancel out. And here we have the conversion factor of mole to mole ratio. We have millimoles of water. How many? 1 millimoles of water. This is 1 water molecules. And in 1 water molecules, we have 2 hydrogen. In this case, 2 millimoles of hydrogen. So the millimoles of water cancel out. Give us our answer in terms of millimoles of hydrogen. And again, divided by the lowest number of mole, 0.0752. 0.0752. Of course, this gives us 1.5 again, and this gives us 1. So to get rid of that 0.5, we multiply by 2. That gives us 2, and that gives us 3. And we have the same answer as above, which is C2H3. Isn't that easy? We don't have to convert milligram to mole and convert back. So that's how you can manipulate units that are not in terms of the base unit. So let's look at another variation of this problem. A combustion of this compound consisting only carbon and hydrogen, causing a 3.31 milligrams increase in the mass of carbon dioxide absorber and a 1.03 milligram increase in the mass of water absorber. So it's similar to that problem. So it's the same problem. Now I'm just adding something extra. The compound was further analyzed and found to have a molar mass of 54.10 gram per mole. What is the molecular formula? So going back to find the molecular formula, first of all we need to find empirical formula, which we have right there. Why do we need empirical formula? We need to find the molar mass of empirical formula. So here I have the empirical formula, and the molar mass turned out to be 27.05. And once we have the molar mass, we can plug into this equation to find the multiplier. Molar mass of the molecular formula divided by the molar mass of the empirical formula to give us that whole number ratio. In this case, if we plug this in, that is going to be 54.10 divided by 27.05, and that will give us 2. So in this case, we take this multiplier and time the subscript of the empirical formula, which is 2 times C2H3, give us C4H6, and that would be our answer.